Hi, I'm Kenneth, the machine learning engineer from Algomo, and in this video I'll be talking about our project with ELSA, which is Addressing Hallucinations in Conversational AI. A little bit of background about us. We are a multilingual customer support platform powered by generative AI. This effectively means we create customer service chatbots for our clients. The central problem facing generative AI right now is hallucinations, which are responses generated by an AI that contain incorrect information, but they are presented as fact by the AI. This degrades trust in the AI outputs, and it represents a huge restriction on applicability of generative AI on industries like medicine or the legal industry. In this project, we have 5 objectives. Starting with improving our models in terms of the hallucination rates, we then want to incorporate these improvements into the product. Then we want to disseminate the results, increase revenue, and raise funding. Throughout the project, we've developed 3 solutions. First is Agent Assist. This is a feature where the chatbot would suggest an answer to the customer service agent to use, rather than using this response immediately in a fully automated conversation. Secondly, we have an observable AI solution, which is a hallucination detection system used for detecting hallucinations. This is very useful for alerting us when hallucinated response is generated, or to measure our hallucination rate over time. Finally, we have modular composition, and I will be going into more detail in this later in the video. Let's dive a little deeper into Agent Assist by going through an example. We'll start with a question: where is my nearest network branch? This question is passed into a generative model, and then provided some information from a knowledge base, the generative model would then generate a suggested answer. This suggested answer is presented to a user of our platform, which would be a customer service agent, and this user can then choose to edit the response or use it as it is. If an edit is made, we end up with a positive and negative example, and these examples represent training data for a human preference model. The human preference model would learn to predict what a human would prefer the answer to look like. And this model can be used to perform a reinforcement learning update on the original generative model. The whole thing is a feedback loop, where the more users use our platform, the more data we end up having, and the better our human preference model ends up, and the better our original generative model becomes. Currently, we've implemented the feedback loop, all the way until this green section, and we are currently collecting these training examples so that we can eventually train the human preference model. Our next solution is a hallucination detection system. This is composed of online and offline metrics, where online metrics are metrics that are computed by a monitoring solution provider, while offline metrics are metrics that are computed on our application servers. As you can see here, the online metrics are mostly LLM based. LLM based metrics are more powerful in the sense that they can detect more vague and complex types of hallucinations. But at the same time, these metrics are also vulnerable to hallucinations as well. So these metrics are powerful but more noisy. On the other hand, the offline metrics are more programmatic. So for example, with the regex entity extraction metric, we extract links and emails from the answer via string patterns, and then we compare the entities within the answer against the source material. If the source material does not contain one of the entities used in the answer, then we flag that generated answer as a hallucination. So let's walk through an example input and generated output using this metric Raga's faithfulness. In this example here, the customers complained that their subscription was cancelled, but then they were still charged for it. In the generated answer here, it's mostly correct, but there is this one claim if you haven't downloaded any resources within 30 days, you can request a full refund. This claim is not supported by the source material shown in the bottom left, and therefore our Raga's faithfulness metric shows a very low score of 0.2. Our final solution is modular composition, and I would like to start with looking at traditional retrieval augmented generation, or RAG. In RAG, we start with an input question, we search for information to answer that question, and all of that data is passed into an LLM which would generate the final answer. There is a fundamental trade-off here where the powerful models are smarter and less prone to hallucinations, but they're also costlier and slower to run. The goal of modular reasoning, the first part of our solution, is to optimize this trade-off by splitting the answer generation process into a planner and a writer module. The main difference is that the planner module outputs a brief answer outline, which the writer takes as instructions in order to write out the full answer. Because the answer outline is very brief, we minimize the output of the very powerful model of the planner. At the same time, the planner also gets to instruct the writer on what to write, which means the answer is generally more helpful and it uses a more relevant subsection of the data. Splitting the planners from the writers also enables us to specialize writers based on the type of response it's generating. For example, in the illustration here, we have three situations: when an answer is found, when an answer is not found, and when a question is not relevant and should not be answered. Each of these writers get a different set of instructions, which means each writer is more faithful to the instructions, and we have less occurrences of, for example, when an answer cannot be found, but the LLM still generates an answer anyway. That's a very common hallucination we find in RAG. So after 6 months, we've managed to improve our models in the sense that our end-to-end question answering system has a lower hallucination rate. We've managed to incorporate everything into the product. We have disseminated the results somewhat via social media, but we have not yet published a research paper. We've increased revenue by increasing the number of users of the product. And finally, we've managed to raise £1.3 million of funding via grants. On some of the challenges that we've faced throughout the project, one of them would be the poor instruction following ability of LLMs, particularly when it comes to complex tasks. The way we've tackled this is to break down the tasks into simpler subtasks and to avoid complex instructions as much as possible. So this would be the modular composition solution that I presented earlier. Another issue that we've faced was the hallucination detection accuracy being very low. So this is because hallucinations come in many different forms, and it can be a challenge to develop a metric to detect, well, all of the different forms. What we've done is to isolate the different patterns of hallucinations, for example with the regex entity extraction metric earlier. And using ensemble methods, we aggregate all of the different metrics into a singular true or false flag at the end. Finally, we also found it a challenge to keep up to date with new model updates, because with every new model, we essentially need to rewrite all of the prompts. What we found very useful was to avoid prompt overfit, which means to avoid any prompting techniques that are specific to a particular model. And we also develop a bunch of different test sets for each task, with different scenarios for each. And this makes it very easy and quick for us to evaluate a given model and prompt combination. This project has had a very high impact on Algomo. For example, we've seen an 86% resolution rate, which means 86% of customer support conversations being fully automated. We've also seen higher product adoption in terms of number of users, new users for our product, and we've also seen lower inaccurate answers in the last few months. In terms of next steps for Algomo, we want to move towards AI agents, which are AI systems that can interact with outside systems, for example, to fetch live order statuses. We also want to improve our hallucination detection metrics and to complete the human-in-the-loop work with Agent Assist. Thank you very much to ELSA for supporting us during this project. I would also like to thank Nikhil Patel for his contribution to our observable AI solution. Thank you for listening.